Good day, friends. Let's continue to solve problems on impulse and momentum. Problem statement goes like this. A particle of mass m1 collides with a sphere of mass m2. The direction of the motion makes an angle alpha with the normal to the surface of the sphere. At what angle to the normal will particle bounce off if the sphere was initially at rest and the collision is elastic? So instead of m1 and m2, I chose different letters, just m for small sphere and large M for the larger sphere, yeah, which just means their masses are different. So basically, in the beginning, it's at rest, and the small sphere approaches this large sphere and then hits off its normal and then bounces off at different angle, yeah, and this large mass has to move definitely, and definitely you know that we are going to apply the vector laws. Yeah, we have told about it last videos. If you didn't watch it, please go and watch them to understand this problem better. As we have told you before, we have several vectors, and let's call this vector A, and this is our momentum one. We work with momentums, not the yeah, this is a vector. We are working not with just velocities, and we have told you that in this kind of case, we have to work with momentums because the masses are not the same, and we cannot work only with velocity because vectors do not depend only on velocity, but the masses as well. Yeah, let's call this some B vector. It is our second momentum, and C vector, which is our third momentum. Okay, yeah. And as you can see, in the beginning, we're not given any velocities, but we can give the meaning to them at the very beginning, hoping that at the end we just get rid of them, of all of them, yeah? This is, let's call it just V1, let's call it just V2, so it was convenient to us, and let's call this V3, yeah? Okay, so as you can see, yeah, as we have told you before, we can work with vectors, and it is pretty convenient. We can use sine law, cosine law, which we are going to do today. And if you look at this one, this vector, this is the main vector which creates other two vectors, which is this one and this one. We can go backwards, say this and plus this vector, they create this one. This will be as our resultant vector, even though in fact it was the main vector at the very beginning. The backward approach works as well. Yep. So I can take these and show you. Yeah, let's take with the arrow at the very beginning. Yeah, let's put it somewhere here. Let's take our two vectors, C and B, that we are going to work with. So if you remember, we can take some, if we want to add some vectors, yeah, if we want to add some vectors, then we would see that we can just add one of its heads to another's tail, and yeah, we can just take this out, yeah. This is, oh yeah, I forgot the arrow above because momentum is vector quantity. This is very important to note. And the resultant vector would be what? The resultant vector would be the beginning of the first one, and the end of the second vector is our resultant vector. And as you can see, it works pretty good in our case right here. Yeah. So as you can see, we have several vectors, and yeah, this was the beginning and the end of the first vector. And if we want to make addition between two vectors, we need to add the end, the beginning point of the second vector, and the end point of the second vector would be our final point. And if we take the first point and the last point between them, that thing would be our resultant vector. Yeah, okay, good. I hope you understand it well. Okay, right now let's try to understand which of them is which. Well, if you look at this, yeah, the parallel line, it does not matter. Yeah, this one, not parallel, I'm sorry, a straight line with x-axis. And these vector, which is C vector, their angle is beta. It does not matter where is it, maybe this here, maybe at that other end. And you can see definitely this is our C vector and this is our straight line. Then it means that this angle has to be our beta. Okay, let's write it here with the green one. So this is our beta. Oops. Yeah, like this, yeah. What about our alpha? Well, if you look at this again, this would be pretty intuitive. This is again straight line, and the angle between straight line and our A vector is our alpha. Well, if we look at this, well, you can see that our vector goes like this, yeah? But instead, we can draw the hypothetical beginning of this vector like it was approaching from somewhere, like this. Yeah, then you can definitely see, yeah, also I can do the same for this one. Yeah, so definitely right now you can see that this is the straight line that we were talking about, and this is that A vector that we were talking about. So this was our alpha, and let me note it. This was our alpha, and if this is alpha as well. Yeah, we know that thing. That's why just let's take it off. Yeah. Okay, right now we know two angles. We don't know the meaning of this angle. We can call it 180 minus beta minus alpha, but let's not complicate it. Yeah. Okay. Or Or maybe, just maybe, it would be pretty convenient to us, maybe using the sine rule, but I would right now use my favorite cosine rule, yeah? So if you remember, if we want to work with some angle, if we want to work with angle alpha, we are going to work with something what is opposite to it, which is our c vector. If we are going to work with our b angle, beta angle, our main angle would be, main vector would be our a vector. Okay, let's see, let's write the equations for both of them, why not? If you remember, our rule goes like this. Let's write it for alpha first, yeah? So our result has to be c vector, which is third momentum, yeah? So it must be something like this. Yeah, let me write it totally. C vector equals a and b, a squared plus b squared minus 2ab and cosine alpha, because we are working with alpha right now. Okay, and let's open them up. C vector is our p3 squared equals a is our p1, and that thing is p2. P1 equals, P1 plus P2 squared minus 2 P1, P2 cosine alpha. Okay, good. And let's open them up again. These are momentums. This is important. So what is the meaning? The first momentum is not just V1, it's mv1. It's small mass and its velocity. The third one, yeah, this one, is again trajectory of the small mass and its last velocity, which is here. And this one is not just V2, it's the huge mass. This is important to note. And V2. Okay, so let me write it here. It would be mv2. This thing has to be small m v3, and the first, at the very beginning, it has to be small m and v1 squared. Oh, v1, yeah, I'm so sorry. Okay, good. We're working with third momentum, which will be this thing, yeah? So it would be something like this. M squared v3 squared equals momentum 1, momentum 2. These has to be just m squared v1 squared plus m large v2 squared. This is squared as well, yeah, and minus 2 mm v1 v2. Yeah, good. This is cosine alpha. Okay, good. This is a very important thing to note, and let me highlight it like this. Another thing, let's continue. Right now, let's work with beta. For beta, a is going to be our result, a squared, and definitely this will be just rest 2, which are b and c, minus 2bc. This will be cosine beta. Okay, and our a is small m, v1. These are squared. This is important. B and c are these, yeah? So it's just, again, that m1 squared, v3 squared, and this has to be large mass, v2 squared. This is squared as well, minus 2, again, m1, okay, yeah, not m1, just m. Yeah, I'm so sorry. It's just m, v2, v3. This is important. This is cosine beta. Okay, good. Yeah. So yeah, it had to be at the very beginning, it had to be our a vector is our first momentum squared. If you don't understand what we did, and b vector was our p2, as you can see, p2 squared plus p3 squared minus 2p2 p3 cosine beta, and that's how we got this thing. If you get distracted, this thing is this one, p2 is in fact this thing. It does not matter if we change positions, this one, and this whole thing is this one, yeah, because p2 gives us mv2, p3, I'm so sorry, P3 gives us m small and v3. P2 gives us this mv2. Cosine beta is just from formula. Oh, yeah, let me highlight it as well. Okay, good. We have two equations. Which is pretty convenient. Good. Right now, what we can do is something like this. We can collect those masses to one side. Also, we can, yeah, let me take these to collect one side and also these to that side as well. So what we're going to be left with is something like this. Let me choose red maybe. Okay, m2 comes out. Yeah, maybe, just maybe, I should take it, copy it somewhere here, and continue work. Yeah, this would be m squared, v3 squared minus v1 squared, because I just took it and moved there. This thing is minus as well. This is m squared v2 squared. Okay, this thing is right now minus 2 mm v1 v2 cosine alpha. Okay. What about this one? Let's work with this one. Let's write it very close to it. The very same principle, as you can see. I believe it's got to be something very interesting. Okay, v1, v3 as well, minus m squared v2 squared. Is it the same? No, it's not the same, because here we see v3 minus v1 squared. It is v1 minus v3 squared. But the rest thing is probably the same. m v2 v3 cosine beta. Okay, let's draw it in red. Yeah. Okay. Good. right now, what we're going to do, we're going to write the conservation of energy. Yeah, we know it. The conservation of energy rule, you probably remember it. Sum of energies at the very beginning equals sum of energy at the very end. And the very first energy is, the total energy is this one. Yeah, kinetic energy of this small ball. And energy is not vector. That's why we don't have to break it into components. Then this whole kinetic energy transfers into two different kinetic energies, which is this one and this one. That's why our equation would look like this. Energy, it would be what? mv1 squared divided by 2 equals this small mv3 squared divided by 2 plus m large v2 squared divided by 2. And we can cancel these out. Okay, good. We can collect masses to one side. Yeah, again, this, even if this thing goes to left side, this thing goes to right side, it does not matter. It will not be minus. It will be plus, because with the meaning, this is total energy, then it splits into two halves, which is this one and this one. Yeah, okay, good. And that's the meaning of this equation. Okay, let's collect masses to one side. It would be what? It would be v1 squared minus v3 squared equals mv2 squared. Okay, I like it. And as you can see, we have the meaning of it. I can write it like this. Minus v3 squared, and this whole thing will be just mv2 squared divided by m. Okay, and right now let me highlight it with some different color, maybe green. And this is something very useful. If you ask me why, we have the very same thing in here. And in fact, we can say we have the same thing in here. Yeah, okay. Right now we can change all of the we can multiply everything by -1, and then we will have something like m2. These two would change positions. This would be something like this. This turns into plus m2 squared v2 squared equals, this thing will be also plus m v1 v2 cosine alpha. Okay, good. If I paste inside of that v1 minus v3, both are squared, this thing, then we would have something like this. This must be m squared here. Also multiplied this mv2 squared divided by m plus m2 okay, this is squared, and then this whole thing, 2m mv1 v2 cosine alpha. Good. Right now, let's cancel these out. Okay. What else do we have? Okay, as I can see so far, mv2 squared comes out as a common factor. Here we are left with small mass and one of the large mass. Yeah, why? Because we have square in here. Only one of the masses comes out, but the second mass stays in. Yeah, this is not h. Sorry for my writing. It's m like this. Yeah. And maybe just, yeah, good. I think that's pretty good. This thing's got to be 2m v1 v2 cosine alpha. Okay, and right now, what can we do? We can just cancel one of the masses, v2 and v2, and I believe the meaning of the cosine alpha is found right now. Okay, meaning of cosine alpha is something like this. It is what? It is m plus m, and outside of the brackets it is v2, and below we have 2m v1. Okay, this is the meaning of cosine alpha. Okay, let's keep it. I believe it's got to be something useful to us. Yes, good. And right now let's do the very same thing. In fact, we don't have to multiply everything by -1 because we have already this form v1 minus v3 squared, that form already ready. Yeah, this is this one multiplied. We can again change this into v2 squared divided by m minus m squared v2 squared. The very same thing, minus 2m v2 v3 cosine beta. The very same procedure. This cancels out. That m v2 squared comes out. This is m left inside. One of the m's also stays inside. This thing is minus 2m v2 v3 cosine beta. But oh, okay, yeah, we can cancel this, and if we want to get rid of this minus, we can just change the positions of these two. Yeah, then it would be something like this. Then it would be what? It would be v2 here, m minus m, large M minus small m. This thing becomes positive. It is 2m v3 cosine beta. Well, basically we multiplied everything by -1 again to make it positive. Yeah. And the meaning of cosine beta is found as well. It is large mass minus small mass. This is v2, and here we have 2mv3. Okay, something very close to that. Okay, good. And that's pretty intuitive and pretty logical. Okay, I like it. Okay, yeah. We were meant to find the meaning of the beta, and let's try to find it through tangent. We can find it through sine, cosine, but I believe finding tangent would be the most useful way. And let me show you why. I have some idea. Okay, it goes like this. Well, if we want to find the meaning of tangent, it must be tangent beta. Yeah, our final answer will be in tangent beta. Well, we definitely know that tangent beta opens up as sine beta divided by cosine beta. Okay, we have the meaning of cosine beta, which is here. That's not a problem. The problem is about cosine alpha. Okay, we don't know the meaning of sine beta. We have the meaning of cosine alpha. That's why it means that somehow, just somehow, we have to connect it to cosine alpha. Okay, let's see. I believe that I can move to sine beta, from sine beta to sine alpha. How do I do it? Just the law of sines, yeah? We can do it sine alpha and something opposite to it. Okay, if we have alpha, then our c vector, or p3, yeah? p3 vector is below, and it would be sine beta, and what we have here, beta, we have p1 vector, yeah? Or instead, some people write it like this, some people write sine below and opposite value above, but it does not matter. It does not change anything, in fact. The main principle is like this, yeah? You know this. I hope that you know the meaning of sine rule. Well, right now I can change this sine beta to sine alpha and somehow to move to cosine alpha. Okay, to find the meaning of sine beta, it would be what? Sine beta would be equal to what? It is sine alpha multiplied, p1 goes above, and p3 stays below. And right now, we can substitute it here. Sine beta has this kind of meaning. It is sine alpha below cosine beta stays, and this would be p1 divided by p3. Okay, good. What else? Sine alpha, okay, I see it. We can move to cosine alpha. How? We know that, maybe I would write it maybe here, yeah? We know that tangent alpha equals to sine alpha divided by cosine alpha, right? So I can write it as sine alpha equals tangent alpha multiplied cosine alpha. Okay, right now you probably see where I'm going with this. Yeah, sine alpha is tangent alpha multiplied cosine alpha. Then this thing has to transform once again. Let's bring tangent maybe here, and above let's make it cosine alpha. Here is cosine beta still stays here, and it would be p1 divided by p3. Okay, good. I like it. And right now we have all of the values. Tangent alpha, let's leave it like that. Why not? And meaning of tangent beta would be tangent alpha multiplied. Okay, cosine alpha. It is this thing. Okay, let's write it here. M plus m. V2 is outside, I believe. Yeah, V2. Yeah, 2mv1. It is 2mv1. 2mv1 divided. This whole thing is cosine alpha. Only cosine alpha. Cosine beta is like this. 2mv3 below, and that is okay. Here we have m minus m, this is v2, and divided by 2mv3. And multiplied, here we have momentum 1, momentum 3. Momentum 1 holds the meaning of mv1, momentum 3 has the meaning of mv3. Okay, it is mv1, this is mv3. Okay, good. And right now, look at this. v2 cancels with v2, 2m cancels out with 2m, yeah, and m cancels out with m, and as you can see that this thing is in fact above, and that's how we can cancel these v's. We can cancel out v3 and v3. Yeah, and at the end, as you can see, we have just this kind of answer. Yeah, maybe I should write it below here. Yeah, so tangent beta has answer tangent alpha multiplied m plus m, m minus m. Okay, yeah, this is the answer of our problem. Good, I like it. As you can see, in fact, it is not that hard. It is pretty intuitive. Yeah. Just you should learn how to draw these vectors, how to use it. We just applied cosine law just 2 times. Here, simple math a little bit, and then yeah, we have found the meaning of this thing. We have substituted through conservation of energy, which is here, yeah. And we applied it to both situations where we could find the meaning of cosine alpha and cosine beta. And then we wanted to find the meaning of tangent beta, because beta is exactly what we were searching for so far. And then through simple math, we just moved to this answer: tangent alpha, cosine alpha above, cosine beta below, p1, p3, and then at the end, as you can see, a lot of stuff just cancels out, and then we would have this kind of very beautiful, simple answer. Yeah, I hope that you understood this problem. If you didn't, you can write me privately, and I will try to explain it to you as best as I can. Okay, thanks for your attention. Goodbye.